Hello and welcome to this video on data integrity. It's 6.2 in the CIE 9618 Computer Science A-Level course, and there is a set of videos on Past CS for the course. Please check out the rest of the videos. So in the last section, 6.1, we saw that it's important to keep data secure so that it couldn't be damaged, lost or stolen. And in this video, we look at how it's important to make sure that the data is integral, or making sure we have data integrity. This is about making sure data is accurate. We have a couple of ways of doing this. We can use validation and verification. Validation means checking the data is reasonable. It doesn't necessarily mean the data is going to be correct. For example, a date of birth of 01/01/1066 is a valid date, but unlikely to be correct if you're applying for a credit card now. There are a range of types of validation, and we can put these into our code in the systems. Things like range check, format check, length check, presence check, existence check, limit check, and a check digit. So all kinds of validation we can do. So a range check checks that data is between two values, so there's an upper and lower boundary. So for example, you might want to check that, the number of days that somebody's going on holiday is greater than 0 and less than 10. Format check. This checks that the data follows a format that we know. For example, dates might be in a DDMMYY format, and if one of those things is missing, then we know there's a problem with the data if it doesn't follow that format. A length check checks that data is a reasonable length for whatever the data is. So for example, for a credit card number, you would expect it to be 16 digits long. A presence check checks if the data has been entered. In other words, the data must be entered. If it's not present, then it's not valid. You have to have something in there. You might have something like that for date of birth. If date of birth is so key to your system, you must have a date of birth, then you would say it must be present, it must be entered. Existence check is a little bit different. Sometimes it's confusing between presence and existence. Existence means check if the value that has been entered is a known value, i.e. we have it on a list somewhere, we know what the valid options are. Is it one of those valid options? For example, you might have a whole list of pets that you're allowed to have, like cats and dogs and rabbits and so on, and if you try to put something in that isn't on there, i.e. it doesn't exist on that list, then the data is not valid. Then there's limit check. Limit check is a little bit different to range check. For a limit check, there's only one boundary, and it could either be the upper boundary or the lower boundary. And then check digit's a little bit different. Check digit checks that one of the digits entered is valid by looking at all the other digits. So for example, on a credit card number, the last digit is a check digit, and that digit is not a sequential number. You don't just get the next credit card number that's available. What they do is they look at the other 15 digits in a 16-digit card number and work out what that last digit should be based on that. And that can help against people trying to invent card numbers. If they don't know how the last digit is calculated, they won't necessarily calculate a correct or valid credit card number. And if you mistype it as well, if you type in the digits and you get it wrong, it can detect that you've, in some cases, not always, but it will detect that you typed the number in incorrectly. And then we have verification. Verification can be done at two different stages. One is when the data is being entered, and the other is when the data is being transmitted. So how can we ensure that data is accurate rather than just reasonable? So validation gets us so far, it's reasonable, but how do we know that data is actually right? Well, there's two methods we can use to help, and these are visual check and double entry. So in a visual check, a person, a human, has to manually check the data has been entered against the original source of data. So they look at the original and they look at what's been entered on the system, and they manually check that. They visually look at it and say, is that the same? So it relies on the person noticing that they don't match. And the key thing here is it's done by a person. It's not automatic. The computer isn't doing the check. The human is doing the check. And again, this doesn't actually guarantee accuracy. It just improves the chances of picking up some of the mistakes. And then there's double entry. In this case, the actual data is entered twice, and possibly by different people. The system then automatically compares the two values, and if they're different, the data is rejected. The important thing here is that data is compared automatically by the computer, unlike with visual checking, which is relying on the human. You often see this for passwords and email addresses where it asks you to enter that twice. So it will cut down on some errors, but again, it's quite easy to make the same error twice. Verification during transfer. So when data is transferred electronically, it could be corrupted. We can have interference and hardware faults and so on, which may corrupt the data. So how can we tell that the binary ones and zeros that arrive are actually the correct ones? So the two methods we're going to look at here is parity check and checksum. The idea of a parity check is to see if the number of ones or zeros that arrive matches the number that was sent. There are two approaches that we'll look at: byte level parity check and block level parity check. So in a byte parity check, we look at the number of ones in every single byte that we send. So for every byte that you want to send, you have to add a parity bit. We can use odd or even parity bit checking. For example, this works with, say, ASCII. Original ASCII with 7 bits. The 8th bit could be used as a parity bit. The most significant bit on an ASCII value could be the parity bit. So in odd parity bit checking, what we do is we set the extra bit such that the total number of ones is odd. So if it wasn't odd already, we have to make it odd. In an even parity bit checking, we set an extra bit such that the total number of ones is even. So again, if the number of ones isn't already even in our 7 bits, well, then we're going to set the 8th one so that they are even. So this is what that looks like. So we have the 7 bits, D1 to D7, and then our parity bit at the end there in this example. This is even parity. So if you look at the ones, we have 1, 2, 3, 4 ones in our data, in our 7 bits. So it's already even. It means we don't need to set the parity bit. If the number of ones there wasn't even, say we had 3 ones, then we would need to set the parity bit to 1 as well to make it even. So this is even parity bit checking. And then odd parity bit checking, very similar. We count the number of ones, and this time it's 1, 2, 3, 4. So that's that's an even number. We need to make it an odd number. So we're going to make it 5 instead of 4 by setting the parity bit to 1 as well. So now we have 5 ones in the number, which is odd. And by using these even and odd parity checks on every byte, we can pick up errors. We don't know exactly what's wrong with the data that we're getting in a byte, but we do know that something's gone wrong with a byte. And if we are getting interference quite often on our line or our connection, then we will start to see multiple bytes failing like this. Of course, there can be errors that don't fail the parity check, because if 2 ones, for example, were flipped, then we might be back to where we started and it looks like it's correct. We can also do block parity, and this is where we add parity bits to the row and column in a block of bytes. So in this case, we've got our 4 bytes of data that we want to set. Again, we're sending 7 bits of data plus the parity bit, making 8-bit bytes. So in the rows, we set the parity bits in the same way. In this case, we're using even parity. So in the first row, we have an even number of ones already, so we have a parity bit of 0. In the second row, we've got an odd number of ones, so we need to make it even by setting the parity bit to 1, and so on. But we do the same for columns as well. So if you look down D1, we can see there are currently 3 bits in that column, so we need to add a 1 in the parity bit for the column to make it even. And we do that for all the rows and all the columns. And the corner bit in navy there is the parity of the parity bits themselves. So you can see that we've got a total, if we count up all the row and column parity bits, it's 4, which is even, so we don't need to change that. It stays 0. Now the advantage of using block parity is that we can not only detect some errors, but we can locate some errors as well. For example, if we flip that one bit at byte 3 D4 from what it was to a 1, from a 0 to a 1, then the row parity bit is incorrect and the column parity bit is incorrect. And that means there is an error in that position. So we can actually locate where the errors occurred, not just the fact that an error has occurred. Another method we can use for in-transmission verification is checksum. So for checksum, we add up values for bytes. So we're adding up byte 1, byte 2, byte 3, and byte 4 values. Of course, these are just binary values that we're dealing with. We've written the denary numbers in there. But these are the total values of those numbers. And we add it all up and we get 566 in this case. And then we mod it with 256. So that means we want the remainder. And the remainder in that case is 54. So we divide 566 by 256 and take the remainder, which is 54. So that's our checksum value, and then when we transmit the data itself and the checksum. In this case, we're making sure that it fits in a single byte so that we can send all the bytes plus an extra byte for the checksum. And when it arrives, we're going to recalculate what the checksum should be. So in this case, we transmitted the data, but byte 3 got corrupted. So byte 3 is now 105. We add up all the values this time and we get 438. We mod that with 256 again. Of course, the receiver has to use the same method as the sender. So we've put 182 there instead of 54. So we would get 54 being sent by the sender, 182 that we've calculated as the receiver using the same method, and we can see that they're not the same, which means that something in the data has gone wrong. It doesn't match. So this only detects that something has gone wrong. We have no idea where in those blocks of data that it's gone wrong, but we just know that the error is wrong. Sorry, the data is wrong, so we need to send it again. And that's the end of 6.2. And next time we look at section 7, which is about ethics and ownership.